The selection of a software architecture is no longer a purely technical decision relegated to the initial stages of a project's lifecycle. It has evolved into a fundamental business strategy that dictates an organization's ability to scale, its operational expenditure, and its overall developer productivity. As the industry continues to evolve, the dogmatic pursuit of microservices that characterized the previous decade has been replaced by a more nuanced, spectrum-based understanding of architectural patterns. This evolution is driven by a recognition that distributed systems, while offering immense potential for scale, impose a significant operational tax that can stifle smaller teams and early-stage products. Conversely, the traditional monolith, often criticized as a legacy constraint, is being rediscovered for its simplicity and efficiency, especially when structured with modern modular principles. This video provides an exhaustive comparative analysis of monolithic, microservice, and modular monolithic architectures, exploring their mechanisms, trade-offs, and the strategic contexts that justify their implementation. The Monolithic Foundation. A monolithic architecture is defined by the construction of a software application as a single, indivisible unit. In this configuration, the user interface, business logic, and database access layers are interwoven into one codebase, deployed as a single artifact, and executed within a single process. Historically, this was the default approach for software development, leveraging the simplicity of local function calls and unified data storage. The core mechanism of a monolith is its reliance on a single deployment pipeline. Whether it is a Java jar file, a Ruby on Rails application, or a Go binary, the entire system moves through the continuous integration and deployment (CI/CD) process as one entity. This unity provides significant advantages in terms of initial development velocity. Because all components share the same memory space, intermodule communication is achieved via nanosecond speed function calls rather than millisecond speed network requests. This eliminates the need for serialization, complex API contracts, and the handling of partial failures that characterize distributed systems. Furthermore, monoliths offer the simplest path to data integrity through the use of ACID, atomicity, consistency, isolation, durability transactions. In a typical e-commerce scenario, where an order must update inventory, process a payment, and schedule shipping, a monolithic application can wrap these operations in a single database transaction. If any step fails, the entire transaction is rolled back, ensuring the database never enters an inconsistent state. This contrasts with the eventual consistency and saga patterns required in microservices is a primary reason why many data-critical applications remain monolithic. For startups and small engineering teams, typically under 10-15 developers, the monolith is frequently the most efficient choice. The cognitive load on developers is minimized because they can navigate the entire system within a single integrated development environment instance, utilizing standard debugging tools to set breakpoints that span the entire request-response cycle. This transparency speeds up onboarding and reduces the time to resolve defects. The intercomponent latency is measured in nanoseconds due to direct memory access. The data consistency is immediate due to ACID transactions. The deployment complexity is low because the monolith is deployed as a single artifact. The infrastructure overhead is minimal since the system runs on one server cluster and uses one database. The debugging complexity is low. Single stack trace provides the complete picture of a problem. The challenges of the monolith emerge as the application matures and the engineering team expands. In many cases, the lack of strictly enforced boundaries leads to tight coupling, where different parts of the application become so interdependent that changing one line of code causes unexpected regressions in unrelated features. This structural decay often results in the big ball of mud, a system where the architecture is dictated by haphazard growth rather than intentional design. Scalability also becomes a binary proposition. Because the application is a single unit, scaling any part of it requires scaling the entire thing. If a specific module, such as a PDF generation service, is consuming excessive CPU, the organization must replicate the entire monolith across more servers, wasting memory and resources on the components that are not under load. Additionally, the single point of failure risk is high. A memory leak in a minor background task can crash the entire process, taking the primary web interface down with it. Historically, almost every successful tech giant began as a monolith. Amazon.com in 2001 was a massive, multi-tiered monolith that eventually became so large it hindered the company's ability to release updates. Shopify began as a Ruby on Rails monolith and has famously maintained a monolithic structure even while processing billions in transactions, albeit evolving into a modular version. GitHub, Stack Overflow, and Basecamp are other notable examples of companies that have scaled to millions of users while retaining a primary monolithic codebase. When to choose a monolith? Early-stage startups, when the primary goal is validating a product-market fit and iterating quickly. Small teams, organizations with fewer than 15 developers where coordination overhead is naturally low. Simple domains, applications with well-understood requirements that are unlikely to explode in complexity. Resource constraints, when the budget for DevOps and infrastructure is limited. The microservices revolution. Microservices architecture represents a radical departure from the unified model, structuring an application as a collection of small, autonomous services that model a business domain. Each service runs in its own process, manages its own data in a separate database, and communicates via lightweight protocols like REST, gRPC, or message queues. The defining characteristic of microservices is componentization via services. Unlike libraries in a monolith, which are linked at compile time or load time, microservice components are out of process and independently deployable. This allows a change to be made to a single service, for example, the payments service, and deployed to production without retesting or redeploying the rest of the application. Microservices are intentionally organized around business capabilities rather than technical layers. Traditional monolithic teams are often split into UI teams, database teams, and backend teams. Microservices encourage the two-pizza team rule, popularized by Amazon, where a small, cross-functional team owns a service from cradle to grave, handling everything from the user interface to the database storage for that specific business domain. For massive organizations, microservices solve the coordination bottleneck. When hundreds of developers work on a single monolith, the time spent resolving merge conflicts and coordinating releases can exceed the time spent writing code. Microservices allow teams to work in parallel, making independent technology choices. A team handling image processing might choose a memory-safe language like Rust, while the team handling the primary API uses Go, and the data science team uses Python. Fault isolation is another critical benefit. In a well-architected microservices system, the failure of a non-critical service, such as the recommendations engine in a streaming app, does not prevent a user from searching for a movie or starting a playback. This graceful degradation is essential for systems requiring high availability at internet scale. Here is the summary of benefits provided by microservices for large organizations. Scalability, independent horizontal scaling of specific hot path services. Team autonomy, independent release cycles and tech stack freedom. Resilience, fault containment, blast radius limited to individual services. Agility, compressed release cycles for individual services from weeks to hours. Modernization, ease of replacing or upgrading individual components. The Microservice Tax. The benefits of microservices come at a cost that many teams underestimate, frequently referred to as the Microservice Tax or premium. Moving to microservices transforms internal function calls into network calls, introducing the fallacies of distributed computing. Network latency, partial failures, and message serialization overhead accumulate across service hops, potentially degrading user experience if not managed with complex patterns like circuit breakers and retries. Data management becomes the most significant hurdle. Because each service owns its database to ensure decoupling, maintaining cross-service consistency is difficult. Organizations must abandon traditional ACID transactions in favor of eventual consistency. This requires sophisticated orchestration, for example, using AWS step functions or choreography, for example, via Kafka to manage distributed sagas. From an economic perspective, microservices are significantly more expensive to operate at a small scale. Research indicates that microservices infrastructure can cost from 3.75 to 6 times more than a monolith for equivalent functionality. This is due to the proliferation of API gateways, service meshes, distributed tracing tools, and the need for a dedicated platform engineering team to manage the underlying container orchestration, for example, Kubernetes. Netflix is perhaps the most cited example of a successful microservices transition. Starting in 2009, they split their monolith into over 500 microservices to handle over 2 billion daily API requests. Amazon's move to a service-oriented architecture allowed them to scale their engineering group to thousands of developers. Other pioneers include eBay, Uber, Spotify, and Twitter, all of whom moved to microservices to solve extreme organizational and technical scale issues. When to choose microservices? Large organizations, when you have 50+ developers split into multiple teams. Diverse scaling needs, when different parts of the system have vastly different resource requirements. For example, a high CPU video encoder versus a low CPU settings page. High availability requirements, when the cost of a full system outage is catastrophic. Technical diversity requirements, when different problems are best solved with different languages or databases. Welcome Modular Monoliths, the pragmatic middle ground. The modular monolith has emerged as a powerful countertrend, offering a best of both worlds solution. A modular monolith is a single deployable unit, like a monolith, that is internally structured into well-defined, independent modules based on business domains, like microservices. The defining insight of the modular monolith is that modularity is a function of logical boundaries, not physical deployment boundaries. In a microservices architecture, boundaries are enforced by the network. A service literally cannot access another service's memory. In a modular monolith, these boundaries are enforced through code structure and architectural tooling. Each module encapsulates its own business logic and potentially its own data, often through separate schemas in a shared database. Communication between modules occurs through explicit public APIs or internal interfaces. This provides the organizational benefits of microservices, such as team ownership and separation of concerns, without the distributed systems tax of network latency and operational complexity. The failure of traditional monoliths is often a failure of discipline. Without enforcement, code becomes a tangled mess. Modular monoliths rely on modern tools to ensure that Module A cannot reach into the private internals of Module B. Here are a few examples of such tools. Shopify's approach. They use an in-house tool called Wedge and the open-source Packwork to track dependency violations and enforce domain boundaries. Spring Monolith, a Java framework that validates module boundaries at the test level, ensuring that modules only interact through permitted interfaces. ArchUnit and Endepend. These tools allow developers to write architecture as code tests that fail the build if a module boundary is violated, for example, a billing class importing a private shipping class. Modular monoliths are significantly more efficient than microservices for many workloads. By keeping modules in a single process, The application avoids the overhead of serializing data into JSON or protobuf for every intermodule interaction. In-process calls are roughly 1 million times faster than network calls, allowing for high-performance interactions that would be impossible in a distributed setting. Economically, the modular monolith is often the most sustainable choice for mid-sized companies. It delivers approximately 80% of the modularity benefits of microservices at 20% of the cost. A single server cluster and a single database are far cheaper to manage than a swarm of containerized services. Here are the technical characteristics of a modular monolith configuration. Boundaries are logical and internal, enforced by tools language. Deployment is physical and unified via single artifact. Communication is performed via in-process APIs or internal event bus. Data strategy is based on a schema per module approach in a shared database. Scaling is supported via horizontal scaling of the entire unit. Shopify is the most prominent advocate for the modular monolith. After struggling with the unmaintainability of their early monolith, they chose to modularize rather than split into microservices. They achieved scale by implementing pods, isolated clusters of the monolith, each with its own shard of the database. GitHub and GitLab also utilize modular monolithic patterns to manage their complex platforms while keeping deployment simple. When to choose a modular monolith? Growing teams. When you have 1550 developers and need clear boundaries, but aren't ready for the operational overhead of microservices. Complex domains. When the business logic is intricate and requires strong transactional guarantees. Preparation for microservices. When you think you might need microservices later, building a modular monolith is the best way to find the right boundaries before making them physical. Cost-sensitive enterprises. When cloud infrastructure costs are a primary concern. The Microservices-to-Monolith reversion trend. One of the most significant insights from the 2023-2026 period is the public reversion of several high-profile microservices systems back to monolithic or modular monolithic designs. These cases provide a cautionary tale about over-engineering and the real-world costs of distributed systems. Amazon Prime Video's video quality monitoring service was initially built using a distributed microservices architecture, leveraging AWS step functions and AWS Lambda. While this allowed the team to build the service quickly, it hit a massive scaling wall. The cost of passing high-volume video frames between services through Amazon S3 was astronomical, and the orchestration limits of step functions prevented them from monitoring thousands of streams concurrently. By consolidating these microservices into a single monolithic process running on Amazon EC2 and ECS, they achieved 90% reduction in infrastructure costs, improved scaling capability, moving from 5% of target load to handling thousands of streams, reduced latency, as data was kept in process memory rather than being written to and read from S3. Segment, a data platform, initially adopted a microservice per destination architecture to ensure that a failure in one destination wouldn't block others. For example, they used one microservice for Google Analytics, one for Salesforce, and so on. As they grew to over 140 destinations, the operational burden became unsustainable. A team of 3 engineers spent almost all their time managing shared library updates across more than 140 repositories. When they moved back to a monolith, the results were transformative. Increased velocity. They made 46 improvements to shared libraries in 6 months, compared to 32 in the entire previous year. Operational ease. The worker pool of the monolith was large enough to absorb traffic spikes from small destinations that previously required manual tuning. Simplified testing. A single test suite replaced the fragmented testing of 140 independent services. Istio, the service mesh tool, was originally designed with a highly decomposed control plane, pilot, Citadel, Galley, etc., to follow the microservices best practice. However, they realized that these services were almost always deployed together and managed by the same team. The complexity of coordinating multiple binaries and versions provided zero benefit to users while making troubleshooting harder. In version 1.5, they consolidated these back into a single binary called istiod, drastically improving the operator experience. Technical metrics, a side-by-side comparison. To assist architects in making data-driven decisions, the following table synthesizes the performance, economic, and organizational benchmarks identified in recent industry research. Key insights: team scale and organization. Monolithic architectures are highly effective for smaller teams of up to 10 developers. As organizations scale, modular monoliths comfortably support up to 50 developers, whereas microservices become necessary for larger engineering organizations exceeding 50 developers. Infrastructure costs. Moving away from a standard monolith introduces financial overhead. Modular monoliths typically increase infrastructure costs by up to 1.5x, while the operational complexity of microservices can drive costs up to 6x baseline. Deployment and operations. Monoliths and modular monoliths offer straightforward deployment models utilizing a single unit. Conversely, microservices drastically increase DevOps complexity, requiring the coordination of tens or hundreds of individual services. Performance and consistency. Monoliths provide superior performance with intermodule latency measured in nanoseconds and strict data consistency, ACID. Microservices introduce network overhead, shifting latency to milliseconds and requiring an acceptance of eventual consistency. Resiliency and maintenance. While microservices demand a highly mature DevOps practice and present significant refactoring challenges, they offer unparalleled resiliency. By isolating failures to a single service, they drastically reduce the blast radius compared to monolithic systems. Implementation patterns, transitioning between architectures. Rarely is an architecture static. Most successful systems evolve through several stages as the company grows or as scaling challenges arise. When a monolith becomes a liability, the transition to microservices should be incremental. The strangler fig pattern, popularized by Martin Fowler, is the industry standard approach. In this pattern, new functionality is built as microservices, while existing monolithic functionality is slowly strangled by extracting modules one by one into new services. An essential prerequisite for this transition is moving toward a modular monolith first. If an organization cannot build a well-structured monolith with clear internal boundaries, they are unlikely to succeed with a distributed system. This transition involves code reorganization, moving from technical layers, controllers models, to business domains, billing orders. Database separation, moving from a shared schema to separate schemas for each module within the same database. Interface definition, enforcing that modules only talk to each other through well-defined public APIs or internal event buses. In cases like Prime Video or Segment, where the distribution overhead becomes a burden, organizations may use the consolidation pattern. This involves identifying services that are frequently calling each other or share tight data dependencies, and merging them into a macro service or a modular monolith. This reduces network I/O and simplifies the deployment pipeline while maintaining the internal modularity that was achieved during the microservices phase. The decision matrix, choosing your path. The optimal architecture is the one that aligns most closely with your current constraints and your growth forecast for the next 24-36 months. To determine the best fit for your team, let's examine a few typical scenarios and identify the appropriate architectural pattern for each. Scenario 1, the new MVP or startup. In this stage, speed and lower initial cost are the primary drivers. A monolith is almost always the correct choice. The goal is to iterate on product features, not infrastructure. The team is small enough that informal communication avoids the coordination bottlenecks of a shared codebase. Scenario 2. The scaling success with 1050 developers. When the big ball of mud starts to emerge, the next step is typically the modular monolith. This provides the structure needed for multiple teams to own different parts of the code without the tax of distributed systems. It allows the organization to develop specialized knowledge in specific domains while keeping deployment simple. Scenario 3. The enterprise powerhouse with more than 50 developers. At this scale, the coordination cost of a single deployment unit often outweighs the operational cost of distribution. Microservices become a strategic necessity to allow hundreds of developers to ship features independently. This is especially true if different modules have radically different scaling profiles. For example, global real-time notifications versus local admin reports. Scenario 4. The performance-critical high-volume system. If the system processes high-volume data where millisecond latencies are unacceptable, like Prime Video's frame analysis, a modular monolith or a few very large macroservices are superior. The cost of passing data across network boundaries at this scale often destroys the business case for microservices. Conclusion: architecture as a sustainability strategy. The architectural history of the last decade has taught the industry that there is no silver bullet. While microservices offered a promise of infinite scale and team autonomy, the reality of the Microservice Tax has forced a more pragmatic reevaluation. As of 2026, the modular monolith has taken center stage as the most sustainable architecture for the vast majority of software products, providing the essential benefits of modularity and domain isolation without the crippling complexity of distributed operations. Ultimately, the best architectural choice is the one that reduces the cost of change for your specific organization. For small teams, that is the simplicity of the monolith. For growing enterprises, it is the discipline of the modular monolith. And for global tech giants, it is the decentralized power of microservices. The most resilient engineering teams are those that remain flexible, building well-structured modular systems today that can be decomposed or consolidated as the needs of the business evolve tomorrow. Thank you for watching this video. If you liked it and found it helpful, please smash the like button and subscribe. And if you have questions about the topic, leave them in the comment. Always keep learning. Until next time.